Hi, everyone. I think we'll get started. I'm Micah Wild. I'm here from Sift Science. Today I'm going to be talking about everyone's favorite topic, which is how do you stop your database from going down? So first, a little bit about Sift Science. We help online businesses fight fraud. We work with a variety of companies across a range of verticals, industries, geographies, to help prevent things like people using stolen credit cards, which cause chargebacks, people taking over other people's accounts, people posting spam or other bad content, abusing communities, creating fake accounts. And the kind of service we provide is it's basically an API. Our customers send us data through a variety of different means, either directly from their backend through our REST API, from their users' browsers through a JavaScript snippet, or through a mobile SDK they can integrate into their mobile applications. We kind of ingest all of this data about what their users are doing, if they add items to their shopping cart, if they browse around the website, if they open an app. Finally, when they kind of check out or do some other interesting action, all that data comes into us, into our backend. We store it, and we use that to produce fraud predictions for users. So we basically take all this data into our machine learning system, and out comes a score indicating how likely a user is to be fraudulent. So if you kind of dig into that big box, it turns out it's mostly HBase inside. So we use HBase to store all of the user level data we ingest, which at this point is hundreds of terabytes of data. And the whole process of ingestion and scoring is very, very HBase heavy. We make hundreds of thousands of requests per second to HBase across all of our clusters. And producing a single risk score for a user may require making dozens of HBase calls to pull back all the kind of information we know about the user, to pull back model data, to pull back data about related users that may have an impact on this user's score. And this means that, so why do we choose HBase for this? So back in the day when Sift was first getting started, we were actually a Ruby on Rails app that used MongoDB as our backing store. And as we all know, MongoDB is web scale, but it turned out that wasn't quite good enough for us. We were really hitting the limits of scalability there. So we started looking for alternative databases that could kind of meet our needs for heavy ingestion and high reliability. We settled on HBase for a bunch of reasons. Kind of the main ones were that it was really, really highly scalable. It proved itself to millions of requests per second and petabytes of data, provided strictly consistent reads and writes, which means you know what you're getting. You have good guarantees around the behavior of the system, which is really important if you want to produce a predictable product and give expectations to your users. And it had good support for our really write-heavy ingestion workload, where we're taking in a lot of data from our customers, and we just need to get it somewhere reliably. And finally, it's highly available, at least in theory. And this is really, really important for us because our customers often integrate us directly into their checkout flow. So a user will be trying to buy something on one of our customers' websites, and they hit buy. And in the background, there's an API call going on to Sift Science where we're being asked, how likely is this user to be committing fraud? What's the chance I'm going to get a chargeback if I let this order go through? We have to respond back very quickly and with very high reliability, because otherwise our customers literally can't make money when we're down. And that tends to make them kind of unhappy with us. So we take reliability really seriously. We've put a lot of energy into it. But unfortunately, last year we were having a lot of reliability problems. And mostly this was driven by HBase. So this is our uptime for December. We were down 5 hours for a 99.35% uptime, which is really, really pretty bad. December, as you may know, is a month when people generally like to buy things on the internet. And if you're an online retailer, if you can't sell things in December, like that's just it. That is your business for the year. So this was really bad. We took a look at these numbers, and we decided we really need to put a lot of energy into improving this situation. So we spun up a team that really was focused around reliability, and in particular HBase reliability. And we made really big improvements. So when I put this talk together in April, we were down only 4 minutes. So for the rest of this talk, I'm going to be discussing kind of how we did that, how we went from this really atrocious 5 hours of downtime to 4 minutes of downtime. Those 4 minutes, by the way, were not HBase related. So how do you do that? So the first step is kind of a meta step, is to really prioritize reliability across your organization. Reliability isn't something that happens by accident. It's not something that just happens. You have to really focus on it at every level of the company. It has to be really valued across your company. It's not as sexy to work on as new features or new products. Sometimes it doesn't get that level of attention. But if you really want to make improvements, if you really want to get down to very low levels of downtime, you really, really have to make it a priority for the entire company. In our case, this actually meant spinning up an entire team of senior engineers that were solely focused on improving reliability, and making this really clear across the entire company, to sales, to marketing, to product, that this was our reliability for engineering. And this meant, maybe this feature wasn't going to ship right now. Maybe this product would have to wait till the next quarter, because for now we were going to really, really focus on making sure our product stops going down. So concretely, what do we do to get from 5 hours to 4 minutes of downtime? So the first thing I'm going to be talking about is something called circuit breaking. So the problem we were having, kind of the biggest source of downtime in our system, is kind of what you see in this graph here. This graph shows users scored per second across all of our application servers. What we'd see periodically is that they would just kind of all stop doing stuff at the same time. Generally, if we looked into the application logs, we'd see a stream of errors trying to talk to a particular HBase region server. So, and then we'd go take manual action. We'd shut down that region server. The regions would move to other healthy servers, and everything would recover. As you can see, happens there. But this was kind of surprising, because we have 100-ish region servers in a particular cluster. Any particular request probably shouldn't need to talk to any one of them. We should be able to handle most of our traffic, even if a single region server is down or being slow. So we spent a lot of time trying to replicate this issue in our staging environment. We tried a lot of different techniques to kind of inject problems and faults into the system. We tried killing HBase and HDFS processes, tried killing entire servers, partitioning the network so that our application couldn't talk to a particular region server. And finally, the thing that really worked well was throttling the network on the HBase port. It turns out HBase really needs network bandwidth. If you limit that, you're able to really easily replicate things like, oh, our region server just isn't responding. And luckily, Linux has really powerful network traffic shaping controls. So here we're using the TC traffic control utility to add a ingress filter. Basically, if you run this, you will limit HBase to only 50 kilobits of bandwidth, which, let me tell you, HBase does not run well with 50 kilobits of bandwidth. But luckily, the HBase server is still able to stay in the cluster at this level. So the master won't kick it out, which means you get to sort of extend your test for as long as you want. But one warning, do not try this on your production cluster unless you really, really validated that your system can handle it, because this is really, really destructive. So once we were able to really reproduce the problem, we were able to dig into what was going on. So one of our tools for that was profiling. Here we have a thread dump from YourKit, which is a really powerful tool for understanding performance problems and just generally understanding what your application is doing. So here what we see, this yellow region here is kind of this outage. And what we see here is that during this outage, kind of all of our threads move into a waiting state. If you dig into the stack traces there, they're waiting to talk to HBase. This is a little bit surprising because we have one bad server, we have 100 good servers. We should be able to continue requests. But it turns out actually, because our request rate is so high, we're doing thousands of requests per second on each of these servers. Very, very quickly, basically every server would get tied up, all of its threads would get stuck trying to talk to this single bad region server. And because our timeouts were high enough, they were never able to sort of get back into a good state and do real work. So in order to fix this issue, we turned to a pattern called circuit breaking. So circuit breaking, for those who don't know, is a pattern in distributed systems where clients monitor the health of the servers they're talking to. And if they detect that a server has become unhealthy, they'll just stop trying to communicate with it at all. They'll just immediately fail requests to that server until they've judged that it's become healthy again. So you can see this basically following this state diagram here, where every server starts in the closed state, which is the healthy state. This is all kind of by analogy to an electrical circuit breaker, which prevents, actually I know nothing about electricity, but my understanding is that it stops things from breaking when you have too much power in your system or something. But in the distributed system sense, so we start in the closed state. If too many requests fail, then we trip the circuit breaker, which sends us to this open state. In the open state, almost all requests just immediately fail. We don't even try to talk to the server and risk getting stuck in a retry loop or a timeout. We still allow a few requests through to kind of judge when the server becomes healthy again. If those fail, we just go back to the open state. If they succeed, we go to the closed state and we allow requests again. And to actually do this, we used a library out of Netflix called Hystrix, which implements a bunch of useful kind of reliability distributed systems patterns. So we integrated this into the HBase client library. We tested it out using our artificial fault that we'd created. And it turned out this actually worked really, really well when we have a single region server that's not responding. So here we have users scored per second across two different servers, one without circuit breaking and one with circuit breaking. And what we see is that when we inject this fault, the control server without circuit breaking just stops doing work, but the circuit breaker server is able to recover and continue serving most requests. So how do you actually, how do you actually do this? How do you integrate circuit breaking into the HBase client library? Fortunately, the client library is pretty configurable. You can control a lot of its behavior around connections and communication with the server. So to actually do this, it involves implementing your own, what's called a delegating retrying callable. Basically, it's the code that the client library calls when it actually wants to set up a request to a server. In here, you need to just pull out the name of the server you're talking to, set up a Hystrix command with that server name as the key, kind of the unit of circuit breaking. And then when you're actually making the request, you can wrap it in this hystrix command here, which will kind of enforce this behavior around both timeouts and if the server is currently marked as unhealthy, if the circuit is closed, it'll just automatically fail its request without actually running this call. And then there's a little bit more work you have to do to kind of set up all this, wire it together, and then finally you can set your this custom color conf key in your HBase client configuration to the caller factory you've constructed. Hopefully we'll be able to release some code around this in the future, but I think the code on the slide is kind of enough to get you started there if you're interested in doing this yourself. So circuit breaking, it worked really well to solve these kind of single region server issues, which, if you have 100 servers, you're going to be hitting issues with one or a small number on a pretty regular basis. But it didn't really help us when we had kind of cluster-wide issues. So kind of issues we'd see are we'd hit metadata issues where a region wouldn't be assignable for some reason, or the region boundaries had gotten screwed up and there were a section of keys we couldn't address. Once we had Cloudera Manager just decide to restart our entire cluster, which caused a lot of fun. So these kinds of things cause really bad downtime, and it often takes a long time to recover from them. There's also a lot of tools to fix these kind of metadata issues that aren't safe to be run in the presence of writes. So it's really hard if you want to avoid downtime to kind of take those actions. So to address this, we turned to HBase replication. Our approach was to have two replica clusters, which each replicate to each other. At any given time, applications would only talk to one cluster so that we sort of maintain strong consistency. So once you're in a multi-cluster world, you're back to eventual consistency of that replication. And then if our primary cluster or the current active cluster became unhealthy, we can switch all the applications at runtime to talk to the other cluster. We have a kind of custom connection manager that we've built that reads configuration from Zookeeper about all the active clusters. It establishes connections to every cluster so that the switching process is just a matter of changing the current connection that the application uses rather than having to go through that establishment process. This also allows us to do a lot of important operations. We can do things like full cluster restarts without having to do very carefully managed rolling restarts. We can test out new configurations really easily. We can test out new hardware. So it's been really valuable to us. So we do have So this is kind of what this failover process looks like. We can just flip the switch, and then in under a second, all of the requests are kind of flowing to the new cluster. So this graph shows requests per second to different servers in our fleet. You can see once we throw that switch, request to one server kind of goes down to 0. For the other cluster, it goes up. So the one problem we face with replication is how do we know if it's actually safe to switch to the other cluster? How do we know if it's kind of consistent with the cluster we're currently using? For this, we use kind of a hybrid approach of offline MapReduce jobs to verify the data, as well as online client-side verification. So we've written a custom HTable subclass, which will send a fraction of read requests, non-mutating requests, to the non-active clusters. And it will compare the results of those requests to what it gets back from the currently active cluster. So this we can monitor in real time to determine whether, if we were to switch the clusters right now, how consistent would those results be? And we do this after kind of different ranges of time, from 100 milliseconds to 500 milliseconds to 1 second. to see what kind of delay of replication we're looking at. Final thing we found really imperative to keeping HBase reliable and happy is having a really effective monitoring system. So we use OpenTSDB as our data layer. We love HBase, so we want to use it everywhere we can. And this is kind of what our kind of monitoring stack looks like. We use a tool called xCollector out of Stack Overflow, which runs on all of our boxes, collects application level metrics, collects system host level metrics, as well as metrics from various other services we run, like HBase. We run these on both our region server and our master boxes. It pulls in metrics from the HBase and HDFS JMX outputs and ingests them into OpenTSDB. We use as well something called Boson, which is also out of Stack Overflow, which can read from OpenTSDB and also ingest metric data directly in order to define alerts. So we can be proactively notified when something's unhealthy. And then finally, we use Grafana as a visualization layer to build dashboards on top of OpenTSDB. And that's what's produced all those pretty graphs that I've been using. So some of the things we found really useful for monitoring, really basic one is just the total number of requests handled by each region server. This helps you detect imbalances across your region servers if you have a hot key or a poor region balance. So here we have like this orange region server that's handling way more requests than some of the others. So that's probably something we want to take care of in order to make sure we're taking the best advantage of our cluster. Another thing is 99p latencies. This can indicate all sorts of problems with a particular server. Maybe you have a bad disk or a bad network, or we're on the cloud, so there's a whole host of things that can go wrong with a particular node. And this generally points out things that you need to take a look at. Doesn't necessarily tell you what's wrong, but it tells you that there's something that you should be addressing with that server. Sort of if you see a service persistently high. Another thing we found really important to keep track of is our percent files local. So each region server will report what percentage of the H files that it's responsible for are local to its node, where it can do a kind of direct read to its file system rather than having to go through HDFS. We found that maintain a high locality rate is really, really important for reliability and performance. So we make sure this never drops below like 95% or so for the cluster. If it does, we probably have to do something like a compaction to restore that locality. And then finally, we run HBcheck, which is a really valuable utility to kind of understand the cluster metadata. We run that every minute via xCollector and ingest all of that data into OpenTSDB. So we can find out really quickly if there are like metadata or table assignment issues. And there's a lot of useful stuff out of there. The one we look at most is this inconsistent tables metric. This often will spike if a region is kind of moving around region servers. But sometimes you see something like this, this yellow line at the bottom where this table sort of never becomes consistent. At that point, you probably have to take some sort of like manual actions, like run an HBcheck fix command. So we made a lot of improvements. Things have gotten much, much better. We now have high confidence that we can run HBase reliably. We have some more things we'd like to do. Kind of the next step in reliability is to do cross-data center replication. Currently, we only operate within a single AWS region. So if that region has problems, we're still pretty down. So we'd like to go cross-region to kind of give us that next level. We'd like to automate more of the recovery procedures we currently do manually, like killing nodes that are exhibiting signs of poor performance, restarting masters, which fixes a lot of weird metadata issues, running HBcheck fix commands that can do things like fix region server boundaries. And then finally, we want to do more automating kind of capacity. Today, we still run into some issues when we don't kind of increase capacity at the rate that our data growth is growing or our request rate. So we like to make that more automated. So that's all I have. Thank you. Are there any questions?
Yes, you mentioned that you have a replication. So does it mean that you are running 2 parallel clusters in production?
Yeah, that's what it means.
Repeat the question.
The question was, are we running 2 parallel clusters in production?
And you access randomly or one, or which one is active or both active?
Yeah, so at any given time, just one cluster is active. We have a zookeeper-based switch that controls which cluster the applications are talking to at any given time. So in that way, we maintain strong consistency while we're not in that switching period. Yeah.
What kind of thresholding do you implement for the circuit breaking? In the sense, you don't want to short circuit just because the single request failed. So are you looking at the ratio of successes to failures in a time window? Are you looking at the latencies of those requests?
Mm-hmm. The question was, how do we decide when we should circuit break on a region server? So we have a threshold of like a certain number of requests have to fail before we'll consider it failed. So if there's really low volume, we won't kind of fail inappropriately. And then we have a ratio, which I think is about 60%, if I recall correctly, which we just kind of tuned in our staging environment to kind of give us that kind of level of reliability and trade-off, not failing over inappropriately. And then the other kind of knob to turn is your timeout limit, when you'll kind of consider a request failed. I think we have that set to about 5 seconds.
And what about the threshold for when you consider it to be good after the video?
Yeah, so I can't remember the number we chose, but yeah, you want a certain number of kind of successful requests before you'll allow it to go back to the good state.
Can you talk about how your team has managed this in terms of sort of how many people were working on it, how long it took? Is this something they were working on exclusively this whole time, or was it kind of they were also having to balance other things?
Yeah, so the team as a whole was really focused on reliability for this period, which was about 6 months. Some of this stuff is still ongoing. But I would say like dedicated, that was like 3 or 4 people for about 6 months to kind of get to this level.
Repeat the question.
Sorry, the question was how many people and how long did it take to kind of do all this stuff? I'll say like the replication especially, that's a really big project. We had to learn a lot about HBase replication. There's a lot of kind of confusing corner cases there. But it's been really, really valuable now that we kind of have it running. Yeah.
Do you experience data node failures with any frequency, and how do you address HBase resiliency in the face of data node failures, if you do?
So we run data nodes and region servers on the same hardware. We co-locate them. So those are, for us, kind of the same failure. Although at the kind of process level, we find the data nodes are much more reliable than the region servers. We don't really have like kind of data node process issues, but we do lose hardware on a regular basis. We're in the cloud. Amazon likes to kill our nodes. So that's pretty common. And we find that HDFS recovers pretty reliably. HBase as well, although sometimes it takes a little while for the master to kind of get everything where it needs to go. So that hasn't really been an issue for us.
Have you tried the HBase read replicas?
We have. That was another big effort to improve our reliability, but we honestly couldn't get them to work.
Oh.
We spent a lot of time with a few different versions of HBase, and we just kept hitting weird problems where replication would just stop or the read replicas would just become unavailable, and eventually we just gave up.
Okay. Which version of HBase?
So this was with 9.8 and 1.2, I think.
Oh, thanks.
How do zookeeper knows that which cluster is active? Like
Sorry.
if I have a multiple clusters, how do Zookeeper knows which cluster is active?
Oh, so we actually use a separate Zookeeper from the ones that are actually managing HBase, and we store that configuration ourselves. So we store kind of connection information to all of our different clusters with a flag on one that's currently active, and then our applications watch that Z node in order to figure out which cluster they should be talking to at any given time.
Okay, last question.
How big was your cluster?
So we have a few different clusters which range from like 70 to like 180 nodes. Cool.
Okay, thank you very much.
Thank you.